The next speaker will be Christina Lopano from the DOE NetaLab. She is a research physical scientist with the U.S. Department of Energy National Energy Technology Lab in Pittsburgh, which is part of the Office of Fossil Energy and Carbon Management. She's a mineralogist by training, and Christina uses synchrotron characterization to understand mineral dissolution precipitation and trace metal chemistry to inform environmental stewardship and research management. So, Christy.
All right, thanks a lot. Thank you for having me. I think I was brought here today to give you an idea of how we utilize synchrotron analyses in sometimes very messy applied fossil energy systems. So I'm going to give you an overview of the synchrotron technologies we utilize in the Research and Innovation Center's Geologic and Environmental Systems Directorate, which I'm part of at the National Energy Technology Lab. So just to kind of give you a brief idea of who and what we are part of the DOE National Laboratory System. NETL is the only DOE lab dedicated to fossil energy and carbon management. We're one of 17 DOE labs, and we are focused on maintaining competencies critical to FE mission space. So we're one of 3 applied labs. Like, for example, another of DOE's applied lab is NREEal in Colorado. So as one of the applied labs, our mission space is to provide technology solutions, if you will. But that doesn't mean we can't utilize and do fundamental research, which is what I've been trying to do with my team at NETL since I joined there. As I mentioned, I'm part of the Research and Innovation Center. My directorate, the Geological and Environmental Systems Directorate, is focused on understanding geologic and environmental impacts associated with energy production from fossil energy sources. Members of my team do a lot of research, field-based research, and also experimental analytical. This is where I'm mostly involved, and also geospatial data management and some computational capabilities. So what is a mineralogist doing in an applied energy lab? That's an excellent question, and I'm going to go through some of this, some of what I do over the next couple slides. So when I came to NETL a little over 10 years ago, I began implementing my mineralogy and in turn characterization expertise to a wide range of research projects under the NETL research portfolios. 3 primary areas where I built research projects include some of the following, all of which are deeply based in characterization, particularly synchrotron characterizations. The first of which is studying dissolution and precipitation reactions. What are the geochemical impacts on porosity and permeability? This is particularly something we've done related to onshore unconventional resources like shale gas. And so a first example, also looking at caprock integrity in terms of carbon storage. I particularly have an interest in trace metal point sources, like many people here on the conference, but I'm in turn applying it to studying the impacts on produced water chemistry and also environmental impacts associated with geologic carbon storage and also with disposal of wastes in fossil energy systems. And more recently, my research team has been focused on the effective recovery of critical minerals and REE from coal byproducts. So these are ash materials, underclay. A personal favorite of mine is acid mine drainage. But in order to do so, where we need to understand where they are in these materials. These are not conventional ores. And how are they bound? And so that's where a lot of my research has been in the last couple of years. And we'll talk a little bit more about. For example, this table highlights some of the various synchrotron proposals my team has had over the past 10 years that I've come to NETL. They cover various research interests under the fossil energy mission space, including geologic carbon storage, impacts of onshore unconventional shale production, aka fracking, and then, as I mentioned, more recently, critical minerals and rare earth elements in coal waste byproducts. So it's my hope today that I'll get a chance to go over a couple of examples of some of the challenges, I should say, that we faced over the course of analyzing our samples. I think I'm going to talk a little bit more about what I call the shale scale project, and also the REE related work, because we've certainly come up with a lot of challenges along the way. A lot of times our samples are perhaps not ideal for this type of advanced characterization analysis. However, in some ways, they're the only way we can get some of the information that we're looking for. And so I'm going to go over some of the challenges I've come up with in analyzing these type of samples, and give you maybe some lessons learned and some tips for how to work with these types of samples when you're at a synchrotron beamline. So mostly recently, the primary techniques my team has been utilizing for this work are synchrotron X-ray fluorescence, microprobe, and X-ray absorption near-edge structure, and XAFs if we can. We're not always able to do that due to interferences, which I'll talk about a little bit more, with the overall goal being to determine the binding environment of elements of interest. X or F is utilized to determine where in the sample the elements of interest are located. So in order to do this, we fix the excitation energy, which is something that is unique to a synchrotron. And then we raster over the location in the sample. Then once we find a spot or area of interest, we can then fix the location and scan the energy to collect XANEs and determine the oxidation state in nearest neighbors. Since many of you might be newer to some of these techniques and may not be used to working with specimens that, as mentioned, are far from ideal, I thought I'd take the next couple of slides to go over some of our lessons learned and how we've helped to develop the techniques into our everyday research plans. Hopefully you can learn from some of our challenges. Our first challenge that we often run into is not having enough, having perhaps low concentrations in our samples, especially in the case for our risk assessment studies, for example, associated with carbon storage or with onshore. The example I'm showing here is of Marcellus shale. So we want to evaluate the potential environmental risks so we can avoid future Superfund site situations if at all feasible. One of my colleagues that helped me learn some of these techniques when I was a postdoc, a colleague at the EPA would always joke when we were at the EPS, he'd say, like, your samples are not polluted enough. And so sometimes it's kind of hard to find those areas of interest. And so in order to combat that, we couple as much lab characterization as feasible, which is a good practice just in general, particularly looking at classic sequential leaching techniques. In order to combat the needle in a haystack that we sometimes come into when we're at the synchrotron facilities, we do a couple things. We utilize larger scale mapping. For example, this is a thin section of a small Marcellus shale thin section. This is about 1.5 inches in length. I'm sorry, I lost my scale bar. And we can utilize, this is at SSRL, we're able to go on one of the beam lines like 10-2 or now 7-2 and do a quick scan of basically the entire thin section, and then use some of the map processing to pinpoint areas of interest. We'll then take that same thin section to the microprobe to then have an idea of where to focus our efforts down on the microprobe line, for example, on 2-3. Also, another thing, when you're dealing with the famine situation in terms of concentration of trace metals, detector technology can be key. This is an example. This is a false color map here that is, you guys can't see, there we go, false color map here, where the uranium in Marcellus Shale is indicated in the kind of those orangey specks. We were able to collect bulk zanes on some of the powders of these materials across a wide range of Marcellus Shale samples. And the only way we were really able to do that was because of this 100-element germanium detector at beamline 11.2 SSRL allowed us to collect bulk zanes on uranium and Marcellus Shale down to where we had samples that were pretty low levels of uranium. So the detector technology can be key, and also the beamline scientists have regularly saved the day for us. So utilize them. They've seen just about everything and can help you troubleshoot along the way. A second challenge associated with complex matrices, particularly in applied energy systems, we sometimes have the opposite problem of what I just talked about. In this case, it's a feast situation. Another one of our projects where we want to understand the geochemical impacts of fracturing fluids in shale, where we do think that iron redox can play a large role. This is something we work with quite a bit with collaborators from SLAC, and also with some modeling efforts from LBNL. We're providing some of the fundamental data that is feeding into some of the modeling of these systems. This is a sorry, I have to go over to the other screen. This is a map of the iron signal in a shale core. This is a cross section of a core where we flowed solutions through. This is about 1 inch in diameter core. So we're looking at a cross section. So here we have a situation of what iron spots do we pick? We combat this by collecting multiple energy maps and then perform principal component analysis on these maps. So for example, if I click through, if you watch this map area, I'll click through, we collected XRF maps at these energies in the green lines along the way. So if you watch the map, you can see some of the subtle differences. And this is something that can be done when you have a very stable monochromator on the beam line. And so this is a technique that we utilize all the time in our research. So go ahead and watch the map, and you can see the slight map differences. Oops, I think I lost some of my maps there. As we take maps along these slices. So we then do, using the SMAC software developed by Sam Webb, we then are processing this data on the fly, and we perform principal component analysis on the maps. And so this is a statistical analysis that helps you identify areas of the sample that exhibit the most variation in signal. And so we regularly use SMAC to perform the PCA analysis on the multiple energy area maps along the iron K edge. And this method allows you to pick up on differences you might miss just by eyeballing the different maps. You know, when you just are using your eyes, might lead to sampling bias. So we perform a PCA analysis, and then we select a variety of iron points throughout the map. For example, here's all of these are different points that I selected along the map for collecting microzanes. So now I have a much better confidence that I'm selecting microzanes that will capture any reaction. the reaction front that goes across this from the shale fracture. This is the fracture surface on the top here, down into the matrix. These are some channels that we milled to kind of facilitate flow in the core reaction. So then I perform, after we collect all our data at the synchrotron, we then can perform linear combination fitting against iron standards. We did this in Athena actually this time. And we determined that there are 3 primary iron bearing phases pertinent to the reactions in this sample. We're still doing some work. This is data we actually just collected in March using remote beamline data collection at SSRL, which was a trip in collecting this data from my dining room in Pittsburgh, 2,600 miles away from SSRL. And pretty amazing that we were able to do this during the pandemic. And so I really thank the SSRL scientists for making that happen. But again, this is utilizing SMAC again. We apply the Zane spectra we collected at those like 20 different spots back to the map area to help determine the reaction pathways along the fractures and into the matrix. And so in this case, we can see that there's definitely some iron 3 mapping this ferrihydrite phase. We can see that almost map the reaction front, and it correlates quite well with the leaching front for calcium in the materials. So that's kind of an example of what we do when we have a feast and want to make sure that we are sampling representatively. So probably the third challenge that I'm going to discuss today are when you have a little bit of everything. So this is where you have cases where you run into spectral overlaps. Is this a hot spot? Yeah, you get super excited. Look at my cerium hotspot, and not so fast. I know some of you are probably chuckling. You've had some experience with working with rare earths, and so because of the energies you have to map at in order to see the different fluorescence edges and absorption edges for the rare earths, you often are coming up with spectral overlaps. And in these fly ash materials, in these acid mine drainage materials, we have a lot of overlap. You can have a lot of things at the same spot in the same area, which can then lead to problems when you're selecting spots for analysis, and then when you're collecting the Zanes. And so we circumvent these challenges by data collection strategies. This is data fitting on the fly. So while we're mapping, after we map, we immediately copy over the data, and we do things like MCA fitting, and we do PCA analysis, like I mentioned before. I will throw in here, stay tuned. GSC Cars is coming up with a recently obtained BES funding for a development of a new high resolution detector that will aid in analyzing the diffuse concentrations and the spectral overlaps that you sometimes see. Like these are some points where we have cerium, which is what we are focused on looking at, but there's also barium, or there's also other rare earths or transition metals in the same spots. And so it can make collecting this data very challenging. Here is what I call these my REEal headaches in determining, is it a hotspot? Here's an example of how we deal with that. So the cerium L line at 4839 overlaps with titanium and vanadium and lanthanum, for example. And so what we'll sometimes do at the beam line is collect maps above and below the cerium L3 edge. And then we will perform some map math, again, in SMAC. What we'll also sometimes do is utilize SMAC to correlation plots to help apply things like masks to data to better help us select points. Here's an example of a mask, and you can see that this S4, this bright spot we are super excited about, is actually not able to get cerium signal at that spot. we are able to collect cerium signal at these other spots, S1 and S2 in particular, and S3. So that gives you an idea of some of the data processing we're doing on the fly as we are selecting these points for analysis. So additionally, we've learned with these overlaps, make analysis is already difficult. So we also utilize the MCA data files. These are the XRF spectra that are collected at like every pixel of the sample. So these are dense files full of information. You don't always have to delve into them, but we find that we do. If you don't have a sample where the RE and transition metals co-localize, you're okay for the most part. But we are able to do MCA fitting again in SMAC, and using this fitting, we can deconvolute some of the spectral overlaps and then get a better selection for the cerium points for analysis. So on that note, I'm going to continue on this REE topic to talk to you a little bit about today about REEs, critical metals, and some of the work that my team has been doing with synchrotron analyses related to some different coal waste byproducts. I don't think I'm going to get to talk about acid mine drainage today. I'm going to talk more about coal ash. So there's a fly ash, bottom ash. And so our goal is within our FE mission space is to turn these wastes into something useful. So there is an opportunity has been identified for some of these coal-based feedstocks in order to fill a gap of the domestic RE supply chain, of which I believe 100% of it basically comes from outside the US, most of which from China when you're looking at more conventional ores. So there are a variety of different coal refuse byproducts that we've been looking at. My team has mostly been focusing on coal ash and AMD. What's appealing about some of these is that there's little to no uranium and thorium, and the coal combustion and or mining process often already concentrates some of the materials. So it's almost as if a processing step has already been done. And I throw this on there because this is, I think, a single quote that has been the focus of my enforcing and my research over the past couple of years. And that is from one of my favorite issues of Elements. And this is a quote from one of the papers. The differences in radius, oxidation state, and bonding drive the fractionation of REs in natural systems and enable their industrial separation. And so it's key for robust identification of the REEs in order to, in these coal byproducts, to work smarter, not harder. So we do this, develop methods for sequential leaching of these AMD solids, of these fly ashes, using laboratory techniques, synchrotron analyses that show trends between light rare earths and heavy rare earths. They bind differently in these different underclays, coal fly ashes, and we can then design strategic and selective means for extraction what we want or need. A quick example I'm going to go through is some comparisons of the Appalachian ash versus the Powder River Basin ash. And showing this because about 68% of ash is disposed of as waste. And this is millions of tons of years. And if you think about how many years that we've been burning coal, there is an amazing amount of ash or slag that is just waiting to potentially be harvested. We found that there's different binding natures between the Appalachian ash versus the Powder River Basin ash. We collect map areas of, this is the Appalachian Basin ash. We show results suggest a predominance of cerium-3 with some isolated small particulates of cerium-4 oxides. And so what we're looking at with these microzanes is looking at the two different the cerium-4 will have two white lines as indicated by some of these standards here, as opposed to cerium-3, which will have the one white line. And we use this information and we see that in comparison of the Appalachian ash versus the Powder River Basin ash, we see that the Appalachian-based ash remains 95 to 100% cerium-3. But in the Powder River Basin ash, we start to see a lot more, on the order of 10 to 30% of cerium-4 in some of these ash materials. And these are also much higher in calcium.
Christina.
This is represented in when we do sequential leaching. You can see that the Powder River Basin, you get leaching from down at a much milder pH, as opposed to in the Appalachian ash, we have to take it all the way to the aqua regia in order to get the REs out.
Christina, I'm sorry, we've run out of time. I'm sorry.
Okay, all right. I will wrap it up here with utilizing the extraction and the characterization has allowed us to develop a technique for potentially extracting rare earths from at room temperature using a lot less acid than traditionally used. And this is potential to address legacy, existing and legacy wastes. We actually have a patent pending for an extraction that we've based off of this characterization. And we recently were awarded a technology commercialization fund from DOE to kind of take it from benchtop to a very small scale. And we've got a 50% cost share coming from colleagues out in Wyoming in order to investigate this further.
Okay.
So this has been done with a lot of different researchers and funding sources, and it really is lots of coffee and lots of people to perform this work. So I'm going to end it there. And if there's not time for questions, please send me a note in the chat. I'm happy to discuss further.
Yeah, there are already 2 questions in the chat for you. But
okay, I will
do
check that out.
Okay, so thank you very much.